Hey guys, so in this video we're going to talk about how different kinds of motion give you different kinds of energy. And I'm going to walk you through a comprehensive list of all the possibilities you might see so that for any kind of problem you always know what kind of energy goes with the problem, what kind of energy exists in that situation. Let's check it out. So what we want to do here is make sure that we know which energies go with a particular situation. Now, a potential problem arises when you have point masses. And that's because point masses, if you remember, if they're going a circular path, they have rotational speed. So if you have a tiny little mass here, m, and it's going around a path here, it has a distance little r to the middle, right? And let's say it's spinning that way with an angular speed, w. But it also has a tangential speed, which is linear, right? It's also has an instantaneous speed that's pointing this way. We call this v tan. Okay? So, but does that mean, however, does that mean that it has linear kinetic energy and rotational kinetic energy? It has a w, so does it have a kinetic rotation, rotational kinetic energy? It has a v. Does it have a linear kinetic energy? Does it have both? And the answer is no. Nope. It doesn't have two energies. We only have here one type of motion, so we can only have one type of energy. The object only has one type of motion. It only spins around a central point. Okay? V tan is just the linear equivalent of W. Think of it as like a mirror image, right? If you look at a mirror, there aren't two of you. It's just the mirror is a reflection of you. So V tan is just the linear reflection of W, but there's only one velocity, only one motion, one type of motion, I should say. So if that doesn't make sense yet, that's cool. We're going to do 6 examples, and that's going to cover every possibility. So let's start here. So you have a box in a straight line. Does it have linear kinetic energy? Does it have rotational kinetic energy? Does it have both? So a box in a linear, in a straight line, so something like this, the box is moving. It has a V, so it has a linear kinetic energy. The box doesn't roll around itself or around anything else, so it has no kinetic, no rotational energy, only linear. A disc spinning around itself. So a disc, here's the axis in the middle, the disc spins around itself. Does it have kinetic linear? Does it have kinetic rotational? Every time you spin around yourself, you have kinetic rotational. Now linear has to do with you moving sideways or up and down. Your axis of rotation, I should say your center of mass, the middle of the object has to actually move. If you spin around yourself, the middle never moves. So there is no linear kinetic energy in this case. Okay? What about the Earth spinning around itself? So this is a disk. The Earth is a sphere, roughly, right? And if it spins around itself, it's very similar. There's no kinetic linear, and there is kinetic rotation. There's kinetic rotation because you have a shape around itself. But if you're talking about the Earth around itself, just that part of the Earth's motion, as the Earth spins around itself, it doesn't move sideways. Now, you do know the Earth does move around the sun, but that's a different motion. Here, we're talking about just this piece of it. Now, what about the Earth around the sun? The Earth around the sun, the center of mass of the Earth does move, right? The center of mass of the Earth does move around the sun. So let's draw that real quick. The Earth is doing this. Now, this is where it gets complicated, because you could think of this as, well, the Earth has W around the sun, right? It has a W around the sun, but it also has an instantaneous velocity V. So you could think of this as linear or rotational. In fact, if you solve for it using KL, and if you solve for it using KR, you're going to get the same number, the same answer. Okay? So you could look at the energy either way. The problem is you have to make sure you don't count it as both. What I mean by that is if I ask you for the total energy of the Earth going around the sun, so the kinetic energy of the Earth around the sun, you can't do KL plus KR. Okay? You can't double count it. All right? So here's how I'm going to simplify this. I'm going to say whenever you have an object spinning around itself or around something else, we're going to call that rotational kinetic energy, and we're going to say that there is no linear energy, right? I just mentioned how you could look at it both ways because there's a V and a W. You just can't count it as both. Well, we're going to forget about that. We're just going to make our life simpler and always think of it as rotational energy and never linear energy, okay? Even though you do have a linear velocity going around this thing. So I hope that makes sense. Around itself, around the sun. Now, what about the total energy of the Earth? I'm going to add a little thing here. I'm going to call it, I got C and D. I'm going to call this CD. What about the total kinetic energy of the Earth? Kinetic total of the Earth, meaning the kinetic energy of the Earth around itself plus the kinetic energy of the Earth around the sun. Well, both of these are rotational. The Earth has a rotational energy around itself, and it has a rotational energy around the sun, KR sun, okay? So rotational is if you spin around yourself or if you spin around something else. What about the moon spinning around the Earth? What's the total, what kind of energy does the moon have spinning around the Earth? So here you have to know that the moon doesn't spin around itself, okay? And here, by the way, I want the total energy, And what I mean by that is I want to know, does the Earth spin around itself, and does the moon spin around itself, and does it spin around the Earth? So the moon goes around the Earth. Whoops, what happened? The moon goes around the Earth. Let's just do it like this. But you might know, you should know, that the moon doesn't spin around itself. So the moon only has K moon. As it's going around the Earth, the K moon self plus K moon Earth, the moon spins around the Earth, but it doesn't spin around itself, right? And that's because the moon is locked with the Earth, okay? So the moon is always spinning, facing the same side to us. That's why there's an expression called the dark side of the moon, and it's not really dark. It just means that we can never see it because the moon is always looking at us, right? It's like if you look at a mirror, you can't see your back, you can only see your front, okay? So you should know that the moon doesn't spin around itself, so it only has a rotational energy around the Earth. Now, what about a roll of toilet paper rolling on the floor, right? So you got a toilet paper, it is rolling on the floor, it's running loose, right? It has a V and it has a W, but here it actually has two types of motion. Not only it spins around itself, but it's also moving sideways. So it's doing this. This is called rolling motion. And whenever you have rolling motion, you have two types of energy. So the total kinetic energy is going to be linear plus rotational. So the object actually has both types of energy. This is the only case where you have, out of the 6 that I've mentioned here, where you have linear and rotational. All the other cases you have either linear or rotational, but not both. And in the case of the Earth going around the sun and spinning around itself, it has two rotational kinetic energies, one around itself, one around the sun. Cool? So that's it. I hope this makes sense. This basically covers every possibility, so you should be rocking from here on. All right? So if you have any questions, let me know.